going to look at a second attribute control chart, the C chart. The C chart is used when the quality of a product is evaluated by counting the total number of defects. So for example, blemishes on a product, the number of pinholes, for example, on glass sheets, or the number of holes in castings, for example. And here, in these cases, you could accept a certain number of nonconformities, but the number must be monitored, controlled, and minimized. And the C chart would be then appropriate for this purpose. It's also known as the defect per unit chart or the control chart for nonconformities. And the procedure consists then of selecting a sample unit from the process at regular intervals and counting the number of defects or nonconformities on this sample unit. Again, you need about 25 samples. As before, you need quite a large number of samples to go ahead and calculate the average values. And we have, again, different nomenclature here. Little c is the parameter, the average number of defects per unit in the population, which is to be controlled, so a population parameter, whereas big C is the statistic representing the number of defects in any sample unit. And this is our Poisson distributed variable. Ci is an observed value of the statistic C in any one sample unit, and again C bar is going to be the average over all the observed values, where K is going to be the number of units that we're using to compute the limits. So we'll look at another example of this now. Control limits can be calculated for the C chart. You can see these are getting easier. This is, can you see that? That's a C bar. The center line is going to be the C bar value, this average value over all the units. The upper control limit is going to be 3 over the square root of C bar, and the lower control limit is C bar minus 3 times the square root of C bar. And again, we're recognizing C as our Poisson distributed variable, and the limits are calculated with this 3 sigma limits, where sigma is then sigma C. It stands for the standard deviation of our statistic big C. So, and again, this is also in our textbook if you'd like to look a little more closely at that. But let's look at now an example. We have here a process, it's a laminating press that puts plastic lamination on printed art sheets, which are then cut and finished into sort of a credit card type product. The number of chicken scratches, so little scratches on the laminated sheets, is to be controlled by counting the number per sample sheet. So we're going to use a C chart to control the defects per sheet, so the total number of defects per unit here. And we have, again, 25 sample sheets, so we have different units from 1 to 25, and now we're counting here the total number of defects. So again, what we're interested in is then our C bar value, where we add up all these different CIs, and we're going to divide by K, where K is 25. So the average is then computed, C bar is at 14.1. And the control limits, 14.1 plus 3 times the square root of 14.1, upper control limit 25.4, lower control limit 2.8. Now, it's the same as before. If the lower control limit is 0, then this would be rounded up to, if the lower control limit is less than 0, then you would round up the lower control limit to 0. And here we see our plots. So here again is our data. We have a unit is a 11 by 17 inch sheet. We have the number of defects that we're counting for 25 different units, and we have our lower control limit here down at 2.8, upper control limit at 25.4. And we see again, we are out of control. We have sample 20 here is, I scribbled through that there, has 30 defects, which is above 25.4. So what we need to do then is to identify the cause, find out, remove the cause, make sure it's never going to happen. Then we can remove the point from outside the limits and recalculate the limits, assuming, of course, that all the causes have been rectified. So sample 20 is removed, new limits calculated. We have a new C-bar 13.5, so 13.5 plus 3 times the square root of 13.5 is 24.52. Minus 3 times 13.5, you get 9.82. Now we look at this new control chart, and so we've removed sample 20 here, and what we see in this case is that we have a situation now. So we've got our lower control limit here. There are points below, right? But that's good. So we have to be a little careful here. Low is good. We do still see, though, look at this. Point 15 is still, sample 15 has a value here of 25, which is above our UCL. So we're still not in control. So the same thing has to happen. We look and find out what is the causes of sample 15 being out of control. I mean, it was in control before, but that was when we had a very high point from sample 20. Now with the new control charts, it's still out of control. So the value is removed, and the root causes are corrected. So we calculate a new C-bar of 13.0, and 13.0 plus 3 times the square root of 13 minus 3, we end up with 23 point, let's correct that to 8.1 and 2.8. This is done by Minitabs, it's slightly different there. We end up with this CL of 13.0, and you see all the data then is in control. So now we can go ahead and use these new limits here for controlling our process. And we just want to note the method of calculating control limits for the future by using the remaining data. So we had 25 points, and we ended up only using, in this example, 23 points. This is recommended because often if you take a whole new sample set, it's expensive and time consuming. So if the process is, not so badly not in control, and so you can find the assignable causes and remove them, then it's probably not a bad idea to use these remaining data. However, if you have, for example, more than 50% of the original data has to be discarded because they came from some assignable cause, then probably you should go ahead and take a whole new set of data, having corrected the process, having improved the process possibly. In this particular example, the chicken scratches on these laminated sheets, remember we were looking at for chicken scratches. These are caused by several different factors. There was temperature problems, there was surface condition of the platen used in the press, the pressure applied, the thickness of the plastic sheets, the atmospheric humidity, some of the more prominent issues. And the use of the C-chart enabled the discovery of a few abnormal conditions that resulted then in plots outside the limits. And it also brought about the need for further investigation, because the average number of scratches was really too high even when the process was in control. So then an experiment was conducted to discover the optimal pressure and temperature of the press, and a specialist in plastic technology was brought in to help with the investigation. Several remedies were applied, and the process improvement process went through to improve everything considerably. So, it's maybe an example of a case when the assignable causes were not obvious and required some engineering investigation, which then actually improved the overall process. So just to conclude, we have a few notes about control charts. The meaning of the lower control limits on the P or C chart. It doesn't have the same significance as for the X-bar chart. When a PI or a CI value falls below the lower control limit, it indicates that the process has changed for the better. As we said, lower is good. For this reason, when we recalculate the limits and the remaining data, we don't remove the values below the lower control limit in the P chart or the C chart. But we do have to make sure that if there's any values that are below this limit, they're not due to some faulty measurement or some kind of inspection error. The P chart, for many characteristics, P charts can be used first for several product characteristics in order to identify which characteristic then is critical. We also want to talk about the use of runs. As for measurement control charts, the chart sensitivity can be improved by applying rules pertaining to runs above or below the center line. And so if you see a run up or a run down, the PI or the CI is trending for the worse or for the better, it can be very useful, or especially if there's no lower control limit and you're seeing that the number of P or C is decreasing. And finally, we have the point about rational subgrouping. As in our X-bar and R measurement control charts, proper subgrouping is really critical. You don't want to have some kind of subgrouping that is then going to skew your results. The subgrouping must be done so as to provide leads to discover assignable causes when they are present. So just to summarize everything, we have in the previous section, pen here, looked at the X-bar and R charts, and these are used for controlling the average and variability of a measurement. They're also known as measurement control charts, and the sample size is normally 4 or 5. And here we show a summary of the control chart limits with, again, don't forget we have the tabulated A and D values that come then that depend on the sample size. The P chart and the C chart are then the attribute charts. P chart is looking at fraction defectives in a process, also known as the fraction defective or the fraction nonconforming. We normally have an N that is greater than or equal to 20, and the control limits are given here. The C chart is used for controlling defects per unit, unit length, use an area, and so on. It's called defects per unit control chart. Here we want to have, again, roughly about, there's no sample size, but you want to have about 25 units that you're looking at in order to calculate the averages. And we want to then have our control limits calculated taking the average of the number of counts for all those 25 units. So there are variations on the charts. Those are also in our book. And but in general, this gives you a summary then of all of the control charts that we've covered this far.